Now we will touch base subchannels concept in 16e. Let's understand. So there are three types of subchannels permutations, which is defined, which has been talked about. And there are many more. I mean, they are the most common ones. One of them is called partial uses of subchannel, which is also abbreviated as PUSC, and we have both PUSC supported in downlink and PUSC supported in uplink, and we also have something called adjacent subcarrier allocation, which is called AMC or band AMC, and this is also supported in both downlink and uplink. Now the smallest unit in downlink PUSC is a cluster, and cluster is equals to 14 adjacent subcarriers into 2 OFDM symbol type. So the smallest unit in a downlink PUSC is a cluster. Now the smallest unit in uplink PUSC is a tile. A tile is 4 subcarrier into 3 OFDM symbol. So you can see that in a tile we have 12 subcarriers, and they are distributed over 3 OFDM symbols. In AMC we have the smallest unit called bin, and one bin is 1 subcarrier into 1 OFDM symbols. Now the next level is the subchannel. So in the downlink PUSC, one subchannel has 28 subcarriers. In uplink PUSC, one subchannel has 6 tiles. So we have 4 into 3, that is 12 subcarriers into 6. So that is the number of subcarriers we have in one subchannel of uplink PUSC. And in AMC we have one subchannel equals to 2 bins of frequency domain, and each bin is 9 subcarriers. In the next slide, I will also show how is a subchannel derived in a PUSC configuration. Because we have talked about diversity schemes and how is subchannels how the subchannels are clubbed in a PUSC scheme. So let's start with the top. So we have total 840 subcarriers out of 1024 usable subcarriers, and rest of them are guard subcarriers. So 840 subcarriers are formed into clusters, and each cluster is let 14 subcarriers over 2 symbol times. So now we have left with 60 clusters. Now what we do in the next step is we renumber the clusters. So 20 from the first cluster and 20 from the last cluster were renumbered here in this step. And after renumbering, we do a major groups formation. So cluster number C0 to C11. So there are 12 clusters, and then we have and clusters. So we form actually a major groups into of clusters, 3 major groups, 20, 20, and 20. So there would be total 3 major groups, and in these 3 major groups we will do a regrouping by taking some amount of subcarrier from one group and the second group and the third group. So in major groups we have total 20 subclusters. Out of these 20 subclusters, we will form C0 to C11, 12 of them in one bucket, and then we have C12 to C19, 8 of them in one bucket. So what we'll do is, from the first bucket of major group, sub major group, we have 2 buckets. So in from the C0 to C12 we will take out 6 data subcarriers, and we will also from the next sub, the 8 clusters, we will take 4 data subcarriers, and then we will form 24 groups out of that. Similarly, we will have 24 groups with the next clusters, and in this way. And from these 24 group, we will again take 24 data subcarriers out, and by doing this we will form a subchannel. So first major group will give you 10 subchannels, and then the second major group will give you 10 subchannels, and the third major group will give you another 10 subchannels. So in this way we will get 30 subchannels in 10 meg channel of a PUSC, and each of the subcarrier is not adjacent. They are from different places, and by doing this we actually get advantage of frequency diversity. So let's take let's quickly see the uplink PUSC. In uplink we will have 35 subchannels in 10 megahertz of bandwidth. So the smallest unit in uplink PUSC is a tile, and there are 4 subcarriers into 3 symbol, so that means 12. Out of the 12 there are 8 data and 4 pilot. Now the usable subcarriers 840 is over 3 symbol, and then we will form tiles. So as I said that there would be 210 tiles if we divide them, the 840 subcarriers over a 3 symbol period. So we will form a 210 tiles, and then they would be formed into groups. There would be 6 major groups. Each of the groups will have 35 tiles. So T0 to T34 is group 1, and T35 to T69 is group 2, and similarly we will have a total number of 6 groups. From each group we will take one and one tile, and 6 tiles of these will make a subchannel. So there would be total 35 subchannels. So uplink PUSC we have 35 subchannels in uplink, and we have 30 subchannels in downlink. So we are on slide number 14, and in this particular slide we will also see the data rates that can be achieved in particular combination of permutation schemes. So in downlink PUSC you have 10 mega of channels, and let's say you have an FFT of 1024, so that's an fixed FFT, and we have 30 number of sub channels, and we have 28 subcarriers per sub channels, and there are 4 pilots per sub channel. So there are number of used data subcarriers only is 720, and let's say we have an 2918 as an TDD ratio. So the maximum data rate that we can achieve over 64 QAM 5x6 is 19.1 MB. Now this number is without MIMO, so theoretically we can double the data rate, and it also has an overhead not taken into account. So in uplink, if you see the uplink PUSC, we can reach up to that 8.40 data rate as an 8.40 theoretical data rate, and this particular data rate is without overhead considered, and also the effect of MIMO is not added. The uplink collaborative MIMO is not added here. What I found here is the AMC is a little bit more efficient in uplink in spectral efficiency than PUSC, and one of the reason is that the channels are the permutations, the subcarriers are allocated adjacently, and there are less pilot per sub channels.